It is recording, supposedly. Awesome. But anyway, welcome to the first module of the N2E Robotics Club for this semester. For those of you who may not know, I'm Faith. I'm currently a graduate student in ECE department, working with Professor Dana on like computer vision and robotics, and specifically working on kind of socially cognizant robotics, which is like part of some NSF grant that she got. But basically the goal is like, how can we make robots that take knowledge of human behavior into account when they try to move around? So like, instead of the stop and shop robot that approaches you and then it kind of just stops and beeps and is really upset, one that would know how to, move around like a human. So you walk kind of on the right side of the hallway, or if you're trying to navigate from point A to point B, you're not going to walk through a group of people who look like they're conversing, like those types of things. But in that is kind of where this reinforcement learning comes in, because it's a great way to get your robot agent to kind of learn from its environment, so you don't have to hard code all of these rules. So that's what our first module will be on, an introduction to reinforcement learning. If anyone has any questions at any point, please interrupt me. This should be as interactive as possible. And how interactive can it be when I'm running all the code? But we'll try. Cool. So in general, if you have never heard of reinforcement learning before, it's a type of machine learning where an agent is in an environment and it kind of learns the rules on how to do a task without you having to hard code them. So this image is kind of the basics of everything you need to know about reinforcement learning are right here. So you start with your agent and it's in an environment. And what it'll do is it'll get an observation of that environment, which we call the state, which is represented here by ST. And the T just stands for like a specific time. So at time now. And then that agent will take in the state and say, okay, based on this state, I'm going to execute this action. And then that will percolate through the environment and you'll get different updates based on that. And then the environment will go, okay, here is your new state and here is a reward. And so the reward signal kind of tells the agent how good or bad the action was in terms of accomplishing some task. Let's see. Yeah, so let's kind of ground it in a real life example so that we can understand more what we're talking about. So let's say you are in a room and you want to get like from your bed to the door, right? You are the agent, your room is the environment. And if you have no idea what the task is, then you may not necessarily know, I can see the door right there, so I'm just going to approach it, right? So you can just pick randomly from the amount of actions you have, which will be like, go straight, go backwards, turn left, turn right, let's say. And then you'll do those types of things and you'll get a reward signal from the environment. So that can be anything from a function of your distance to the door, it's usually that. So there's this whole thing with reinforcement learning, which is its own kind of separate topic on how to pick the best reward function. Because if you don't pick a really good one, either training will take forever or sometimes it won't converge to a solution at all. But if you're trying to get from, just where some point in your room to the door of your room, a good reward function would be like 1 over your distance to the door, because the idea with the reward is that it's really high when the agent does something favorable and really low when the agent does something really bad. So if you start walking in the opposite direction of your door, you should get like a very negative reward, like negative 1 billion, right? And if you're walking towards your door, you should get like 1,000, positive 1,000, let's say. Or a good thing or a common practice that people do is they make the rewards negative, because then you can make it just something simpler to conceptualize. So your reward is your negative distance to the door, right? And so while your distance is, while you're far away, your distance is large, and a very large negative number is a really low reward. And then the closer you get to the door, the lower your distance will be. And so a lower negative number is higher. And so it's just kind of easier to conceptualize how we would think of a reward in terms of making it negative for the sakes of the reinforcement learning. And kind of the goal of the agent is to come up with a mapping of what states are good to be in. So for our example of being in your room, kind of what positions in your room are better for you to be in terms of how close you are to the door. So all of the positions in your room that are closer to the door would have kind of a high value in this case, or a higher desirability for your agent to be in. And then the further away from the door you get, the lower the desirability for being in that state. And so a function that kind of takes in a state and tells the agent, well, is this a good state to be in or a bad state to be in, is called the value function. And so there's a whole bunch of math that dictates reinforcement learning in terms of like having it formally defined. And so the value function is kind of just a stepping stone to getting to the final solution of the reinforcement learning agent. But the end goal is basically to learn a policy. So if you know what states are good, then you want to get there. So learning a policy is saying, okay, given the state I'm in, and given the set of actions that are available to me, which action can I take to get me to a state with a really high reward? Because the goal of the reinforcement learning agent is to maximize the reward over its completion of the task. Let's see. Did I say everything? Yes. Okay. So really quick rundown again. You've got your agent in the environment. It takes in a state. It wants to get to states with really high values from the value function, because that means that those states will get it closer to accomplishing some task. So it learns a function where it takes in a state and an action and kind of tries to estimate what the reward will be from the environment once it executes that action. And so it's going to then execute the action that it thinks will have the highest reward because it'll help it accomplish its task fastest. So then the environment takes in the action that the agent just executed, updates itself, gives the agent a new state, and then also gives it an actual reward, which might be different than the estimated reward that's kind of given from the value function. And then based on those, the agent kind of does this iteratively over and over again until it has accomplished some task or not. And kind of the math that I was talking about that defines the reinforcement learning process is called a Markov decision process. I am not particularly good at probability, despite taking so many classes in it and trying very hard. So I'm not really going to go into all of the math behind that, but there's this mostly simple tutorial that I found that you guys can look in if you're interested in that. But before we get into the types of agents, which gets into more like the learning styles for reinforcement learning, let's talk about the environment. Because the task that I proposed earlier of, getting to the door in your room is nice, but it's not very specific in terms of coding up. So what I found is this cool maze environment. And so it's based on this GitHub from this dude. So kudos to him for doing really most of the heavy lifting. I just had to change a little bit of the code to get it to work for our specific purposes. But the kind of background for the environment is that it is based off of the OpenAI gym format. And I have a whole nice module that I taught last semester about that you can go to this link and see, or scroll down to the bottom of the collab, and there's all of the code that I wrote kind of last module to give you a refresher, just in case you want to look at it. But for this case, all you really need to know is we are the blue dot in the maze, or the agent is the blue dot in the maze. You start at the blue square, and the goal is to get to the red square. I think I made it a 5x5 maze, but how big the maze is doesn't really matter. The important thing to know is that like every time I run the code, the goal location will be in somewhere different. So we'll get to see a couple cool behaviors, hopefully. if we pray to the random number generator gods who put the goals in cool locations, we'll get to see a couple of cool things that the reinforcement learning agents will be able to do. Okay, so getting to the agents, I thought we would keep it super simple, which means that we're not really going to get into machine learning today because I feel like we need like a whole first intro module on even what is machine learning and how do you do it successfully before that. So we're just going to go with like really simple Q learning, where the idea is that you're kind of taking the value function, or actually what we call the Q function, but it's like an extension of the value function, and putting it into literally just like a matrix or a table. And so down all the columns, you have just a listing of all the states. So that would be just every square from the maze is represented by one row. And then during the columns, you have all of the actions that you can take. So in the maze, it's forward, backward, left, right. The agent is not allowed to stand still because it's not a real person and it doesn't need time to think. And so then we have an n by m, or an n times m by a matrix that kind of is the brains of our Q learning agent. And at first, the matrix is just filled with zeros because we don't really know anything about our environment. The agent kind of just wakes up there and goes, I don't know what this is. And as it explores the environment, it updates the values in the table based on this formula. And there's a lot of things in this formula, but it's actually not that complicated. So let's start with the last term and work our way forward. So this is where all of the learning happens. So first, an agent will take an action in the environment and get a state, right? And then also a reward from the environment. So we take that reward and then we add to that a discount factor times this term here. And what this last term does is it says, okay, I had an original state, but I took an action and now I'm in a new state, right? So given that new state, I'm going to look through the Q table. So that's like isolating a row in the Q table, and you're going to find the action that corresponds to the highest value in the table, given that new state that you're now in. And then that is the Q value that you're adding here. So you're kind of saying, that kind of tells you what or how good the action that you just took is, because the idea is to be in states with really high Q values. So it's more than just how good is the action that I took for right now, or it's less short-sighted in terms of I'm just going to look at the reward I got for the action I just took and only focus on that. And it allows the agent to plan and really kind of think ahead. So it's trying to make moves that will also put it in a good spot to do well in the future. So the discount factor here that you multiply it by just tells the agent how much or how little to value looking in the future, basically. So if the discount factor is really, really small, so if it was 0, then we're kind of only looking at the present and we're just saying my action was good for right now. And it doesn't matter if I needed to actually do an action with a bad reward because it was the only place to get to a state with a good reward in the end. So it's kind of looking at a long time horizon. So if it was something really high like 1, then it would like really be focused on, okay, I'm willing to take actions right now that have a negative reward because I know that they will lead me to states later that have a positive reward. So that's what this term is doing. It's a balance between learning from the actions you're taking now and then also kind of planning for actions to take in the future. And measuring how good the trade-off between those two things can be. So then you take that learned value and you multiply it all by the learning rate. And the learning rate just says, how much of this am I going to remember in the next step. So if the learning rate is 0, then you're really not learning anything. You're kind of just going through and going, I know I just took a step, but I don't remember anything at all that happened 2 minutes ago. So I don't know where I am in this maze. I don't remember anything. And if it's 1, then you're kind of only learning from like the most recent step. So it's kind of like saying, I have all this knowledge from before, but I'm going to throw it out because what I just did seemed to be good. So I'm just going to keep doing that. So you really want to have it somewhere kind of in the middle of those two things. And then you take, so this kind of term here is computed like every step, but you don't want to change the queue function very quickly because that's going to lead to really unstable training where your network ends up kind of just guessing what the right answer is, just because like the values of the Q table are moving around so much. So what you end up doing is adding this term, which just kind of makes it, when you update the table, it makes it a weighted sum between what was there before and the outcome of the actions that your agent has just chosen to take. So that's kind of what this is. Okay. So then the next important thing to talk about with not just Q learning agents, but all reinforcement learning agents is the exploitation versus exploration back trade-off. So there's this idea that we're using the Q table to say, given this state and this action, like, or given this state, what is the best action I can take in the environment to accomplish a goal, right? But that requires that you already have some background knowledge about the environment that you're in. And if you just got dropped in the environment 2 seconds ago, you kind of have nothing, right? So using the Q table is what we call kind of exploiting your background knowledge. But if you don't do any exploration of your environment, then you have no background knowledge. So there's this whole problem of kind of how do people determine how the agent is going to get this background knowledge. And the way that it kind of does it commonly in Q learning is an epsilon greedy strategy. So we just name some variable epsilon and we make it some small number like 10%, right? And we say, okay, 10% of the time, the agent is just going to take a random action in the environment. And this just ensures that it will basically explore its environment and kind of get some sample data so we can go, okay, if you take this action in this state, it'll be really bad. If you take this other action in this other state, it'll be really good, and kind of get some values to even be able to update your Q table at all. But then 90% of the time, it will be looking in the Q table and use that to actually pick the action to execute based on its state. So that's kind of the naive way to do it. The way that people have moved to doing it now is kind of making epsilon really, really high in the beginning of training. So that kind of you're just doing a whole lot of random actions at the beginning, maybe even like 100% random actions at the very beginning. That way you can get as much information about your environment as possible. And then as training goes on, you slowly decrease epsilon to 0 so that by, I don't know, maybe let's pick a number, by like 100 steps in, you'll be just using the knowledge that you've gained through your exploration phase and only looking in the Q table to pick your actions. So, okay. I guess based on that, we kind of know enough to be able to code up an agent and to see how it works. So, okay, here's my code. And I'll walk you through it. So this is all environment stuff that we're setting up that no one really needs to care about. So you set the number of actions for your agent. We have 4, north, south, east, and west. Unfortunately, code does not really use letters. So this is just represented by numbers. So 0, 1, 2, 3. State bounds is just saying the size of the environment. So the size of the maze. Okay. we are setting our minimum exploration rate and our minimum learning rate. So what we're doing is kind of the epsilon greedy strategy that I was talking about, where we have epsilon be really, really high at the beginning. And then as we get more towards the end of training, it gets a lot lower. So at the beginning of our training, it'll do a lot of random actions, but by a couple steps in, it'll be doing mostly actions based on the contents of the Q table that we make. And then the minimum learning rate is that people kind of do that same strategy with the learning rate parameter, which is this A, which says how much does the new Q value that we just computed, how much is that going to affect our Q table? So how much is the event that we just went through going to affect how good we think the state and the action that we're in is. And so people do the same thing with that they do with the epsilon greedy strategy, where they start it really, really high at the beginning of training because you kind of don't know anything. And so you want to learn kind of as much as you can, as quickly as you can. But then as you get more training samples, you want to decrease that because A, you want to make training more stable. And then B, you don't want to completely erase everything you've learned about the environment based on the most recent training samples that you're getting. Okay, so here we are setting up the Q table, which is really just a matrix, right? And then we click simulate, which goes through the steps of the learning. So I just picked a random number of episodes that's really, really high. So this is just telling it how many times to have the agent try to accomplish the task of getting to the goal in the maze. We're initializing the maze, and then we have code here that selects an action. Basically what it's doing is it's saying, okay, are we going to be picking an action based on what the Q function is telling us to do, or based on random exploration, or following the epsilon greedy strategy? Then this step actually executes it in the environment and then gets the new observation and the reward for the agent to be able to update the Q table. And then done here just says whether the end task of getting to the goal location has actually been accomplished or not. Okay, so with this, we're just keeping track of the reward. And then this is just some processing on the state variable, because I don't think it's in the correct format exactly for us to be able to use it. So then this is updating the Q table based on this equation here. And then it kind of just checks to see, hey, are we in the goal state? Cool, then we're done, moving on to the next episode. Or no, okay, then we're gonna kind of just repeat this loop all over again. Okay, so let's see if we can see it in action. Haha, okay. So we are the blue dot. The maze randomly puts walls wherever it wants, and then randomly generates a goal square. So this one wasn't really that interesting because the goal really only had one way to get there, and it got there in pretty much a straight line. So let's see if we can do this again. Okay, so see, this way it goes in here and it's like really blocked and there's no way out, right? So then it has to kind of just figure out that all of these states have a really, really low Q value. And so it will do that, but at the beginning, it's doing a lot of random actions as well, just for exploration purposes. But as you can see now, it figures out that the Q values are really high for states over here because that's where the goal was. The errors that are popping up are because when I wrote this code, I was not the best at coding, and I did not actually end the program the way you're supposed to end a Python program. I was just like, just break, just end, just quit. And so Python's like, I didn't expect to be quitting now, and I'm reporting a problem. But there is no problem. It's actually fine. Let's just look at it one more time to see if something cool happens. Why does it always want to do the upper right-hand corner? That's interesting. But basically, yeah, it's updating the Q values for all the states over here to be really low and all the states over here to be really high, because that's what leads to the goal. And then this that's printing out down here is just, I had to come up with some metric to use to kind of say, okay, it has learned the optimal solution in the environment. And it was just if it could solve the maze consistently between 2 episodes in like kind of the same amount of time. And if it could do that for 100 different episodes, then I was like, okay, it has sufficiently solved it. It's got it. That was just an arbitrary thing I did for the time. I don't know. Does anybody want to see it again? Or should I move on? Or does anybody have any questions? Also, please feel free to stop me.
All good here so far.
Cool. Then, oh, was there something in the chat? Oh, okay. Ahmed wants to see it again. Let's do it. Yeah, so that's the other thing. I also didn't figure out how to slow it down because I think that would be interesting just for watching it purposes so that you don't feel like it's going a million miles an hour. But yeah, as you can see now, it like really understands that like that's the optimal path. But it's super cool. Yay. Okay. I'm so sorry, Python. I should treat you better. Cool. Okay. We're not done with the maze though. The next part also has a maze, but also I'm gonna apologize in advance for the visualization on the next part being absolutely bonkers, because I tried my best and visualization is not my strong suit. Okay, so the next kind of concept that we can talk about is a different type of reinforcement learning. In terms of a different way to set up the problem. So this is called feudal reinforcement learning or sometimes hierarchical reinforcement learning. It really depends kind of when you got into it. There was a shift where, what year? I don't know what year, but up until some year, everyone was calling it feudal reinforcement learning. And then more recently, people were like, why don't we just call it hierarchical? But they're the same thing. But the idea here is that we are going to try to break down the reinforcement learning problem using temporal abstraction or spatial abstraction. It works the same way, just temporal would be doing this in terms of time and spatial would be doing it in terms of space. But basically breaking down the problem with abstraction in order to make it, break it down into simpler chunks for the agent to be able to solve. Because like, let's say instead of our example problem being trying to get out of your room, the example problem was actually how to get out of your house, right? That could be a whole bunch of different steps. Not only do you have to get out of your room, you have to go down the stairs, you have to like unlock the front door and then like open it and go through it and all of those things, right? And so describing the activity in terms of those high level actions is introducing the temporal abstraction. So the Q agent, the Q learning agent that we just had is not working on that scale because that's kind of the scale that humans are working on. You know, we're like, I'm not gonna, like when you're thinking about walking, you're not like, okay, I must bend my knee 30 degrees and then also now bend my hip by 40 degrees and then extend my knee again. You know, you're just like, I'm gonna take a step. And the Q learning agent is actively thinking in terms of like the angles that it would take in order for you to walk. And that makes all of the actions that you and I as humans would think are really simple actually really, really complicated because the state space is so high. So like kind of the longer time horizon you have on any one task you're trying to get your Q learning agent to solve, the more complex it's going to be without this temporal abstraction. So the idea is, what if we can train a network to think in terms of these temporal abstractions? So with feudal reinforcement learnings, you actually have two networks, one called the manager network and one called the worker network. And so the manager network is thinking like you and I would think in terms of these temporally abstracted actions or these macro actions. So in the maze scenario, let's see if I can get this link. Okay, cool. So in the maze scenario, instead of having like just this fine grained, or maybe that one's too small to think about, but instead of just having this really, really fine grained task that we currently have, we have kind of these two layers. So the manager has just like literally a smaller maze, not in terms of like area, but in terms of number of squares. So it still starts, they all still start in the upper left-hand corner, right? But the manager is thinking, okay, what quadrant is the goal in? So we've broken the maze problem down in terms of spatial abstraction here, um, as opposed to temporal abstraction, which is kind of the examples I gave with how to get out of your house. But functionally, they work the same with the reinforcement learning agent. So the idea here is that the manager will function on this maze here, where it's thinking, okay, what quadrant of the maze is the goal square in? And then it'll come up with some goal vector, some goal signal, and it will give that to the worker network, which is kind of the same Q-learning network that we just kind of went through, that is operating in this smaller maze. So in this case, the goal vector would be what quadrant the manager network thinks that the goal is in. So, if it's in this square, it'll go, hey, it's not in this square. And so maybe try this square, right? And then the worker networks will, instead of trying to get to the goal location as its task, it will just try to get to the quadrant that the manager network specifies. So it will take in, its state, which is just whatever square it's in, and then the goal location via the goal vector from the manager, and it will try to go to that quadrant instead. And by doing that, we get to break down the problem so that the Q-learning agent doesn't have to go, okay, I'm going to search the entire maze for the goal space. It just has to think about getting to where the manager tells it to go. And the manager's task is to find the goal square. So the goal square between this kind of spatially abstracted maze and this lower maze will still be like in the same quadrant, right? So if the goal for the manager is in this one, it'll be in one of these four squares for the worker, right? And so the manager kind of narrows the state space that the worker has to search in order to be able to find the goal, and therefore can find it in fewer steps, basically. Okay, did that make sense? If not, I can explain it again. Okay. Cool. So with that, we can go to the code. The code is like really mainly the same in terms of the setup. So, you set up the environment, you make your agents, you run through the loop of getting your observation, picking an action, executing the action, therefore getting a new observation, then getting a reward, updating your Q function, because we're still using the Q learning agents. We're not doing any deep learning here. And then trying to get to the goal, the maze goal. Yes, it is the same Q agent for both the manager that's kind of coming up with this goal vector, which is the macro action, as with the worker network that's doing the micro actions, which is like actually trying to find eventually the goal space in the kind of more fine-grained maze. The only difference is, where are they? Here. So manager code is like literally the same. It has the Q table, all of the same discount factors that have nothing to do with this. But yeah, same Q table. The only difference is that the worker takes in a goal vector, which isn't actually reflected in any of the code here, but in the code that deals with the environment, the worker is told to go until it reaches this goal location instead of when it reaches the overall goal location for the environment itself. And this goal location will be whatever quadrant the manager specifies. Okay, so I hope that explained it. Let's see here. Okay, so I tried this out earlier, and commenting out these lines did not exactly do what it said that it was going to do, but we will try it and see if we can get it to actually work. Okay, so the setup here is the same. Oh no, I ran the other code and not this code. That might help. Okay, but the setup here is the same. It comes up with a random maze, random walls, and then puts the goal in a random location in one of the quadrants. So this should just, I know, I'm sorry. This should just show us the manager, but that didn't actually work. So I'm not gonna try, right? So I'm gonna run this a whole bunch of times because I really only did it for a 4x4 and then a 2x2 maze just to kind of make sure that the code worked. Oh my God. Python, why? So the idea here is the manager is the big blue dot. The manager starts in this space, ends in that space. With the red, and it really only has 2x2 to search for, right? So the manager picks a random action, goes to a random square, and then says whether it is or is not in the square that it goes to, and then sends that vector to the worker. And so then I will now uncomment out the manager because, all right, let's see if that works. It might. It did not. Okay. So then the worker gets the goal vector from the manager and kind of goes to the quadrant that the manager says it is. All of these random ones are putting the goal exactly at the start point, which is not great for explaining what is going on. Oh, goodness. Okay. Okay. So as you saw at the beginning, the worker was kind of down here because at the beginning, the manager said, hey, try going down here instead. But the only problem with trying to go to the quadrant that the manager says to go to is that the manager doesn't necessarily know where the walls are for the worker. And so sometimes in order to obey the manager, you have to go like completely around the long way, which looks like it's disobeying the manager. And so that is kind of the imperfect thing with our formulation of this temporally extracted experiment, because in theory you're not going to have like that much disconnect between the micro actions of the worker and the macro actions of the manager. um, I really wish I could figure out how to slow down the rendering. That would super help. But yeah, okay, does anybody have any questions? I guess is good to, besides asking me what's wrong with my Python, in which case I don't have answers to that one. Okay. That is perfectly fine. Have a good night. Okay. So that's basically this. And that's feudal reinforcement learning. And so the last thing is Dqns, which, much like Markov decision processes, I'm not actually going to go over because I feel like we need an actual like module to go over deep learning for that so that we understand exactly what's happening, and we don't have time. Also, if you are running just like a regular normal laptop, or like I was when I started, if you were using the laptop you bought in freshman year and it was now senior year and or after senior year, and you're trying to do machine learning on it, you're going to fry it. And it's going to like not hold a charge anymore and get really, really slow. So I would suggest doing most of your machine learning actually in Colab itself, because then you get to just fry Google's computers instead of the ones that you own, and that'll be better. But if you wanted to look into deep Q networks, which is taking the Q networks that we made now with the tables, and just instead of literally making a table, you use a deep network to return the Q value instead. So all of the Q values are learned via a neural network as opposed to being updated by this equation here. But if you wanted to learn more about that, there's this tutorial that I put in here. Here's the OpenAI Gym reinforcement learning environment refresher. If you guys were interested in that, the link to watching me go through it is on our website. And I guess this concludes this module. If you guys have any questions, let me know. If not, thanks for being here. I'm gonna stop recording now.